Now, before I get into strings, I'll finish off a bit on graphs. And you may remember the game we talked about in earlier sessions, very popular in Japan, of paper, scissors, stone. I won't go through it again. I assume you studied it from previous session. But the interesting thing is, you can represent that game using directed graphs in the following sense. Like now, we were talking about this game in the context of a binary relation, right? A binary relation. So with two inputs, like imagine my fist here. That's your function. So and remember a relation. Let's say start with a predicate. A predicate. So that function is called a predicate if its output is either true or false. Okay, and it's a relation if the inputs belong to the values of the inputs coming in belong to the same set. Right? So then it's a relation. And if you only have two inputs, then it's a binary relation. Okay. And so what are the inputs coming in? Well, the set of three possibilities: stone, paper, scissors. Right? And let's say the upper input here is the choice of one of those three from the first player, and the second input is the choice of one of those three from the second player. Okay, and the output then is true if the choice of the first one wins against the choice of the second one. And so here you've now got a directed graph, right? 3 nodes, 3 edges, directed because they're arrows. They're not just lines now, they're arrows. And this directed graph represents the binary relation. In a sense, what is that? Well, we had a list of the ordered pairs that gave the first player winning, beats.
A vast virus database has been updated.
And what are they? Well, you can write your graph in the following form. D is your list of nodes. Well, the three choices. That's your set, right? SC for scissors, P for paper, S for stone. Okay, and I've got a directed graph. Now, why is that relevant to a binary relation? Why does this express the binary relation? Well, the 3 ways that the first player can win is so here's your relation here. Remember from earlier, this R here was the first player beats the second player, right? And so your edges here now are directed, an ordered pair, where X, this choice beats, so the first player's choice beats the second player's choice. So it's there'll be 3 of them. So what is it? So stone beats scissors, scissors beats paper, and paper beats stone. Right? So there are your 3 as a list, and they're your edges. So X and Y are node. They're labels of nodes. Right? So this ordered pair is an edge, and this E here is the set of edges that give you X first player beating Y, the second player's choice. Okay, hope that's fairly clear. Right, so this E here is just the set of ordered pairs for which the first player wins. For which X and Y's give you a win for the first player. Right? Well, they're these edges. Yeah, as I was saying before, let's see. Scissors beats paper, paper beats stone, stone beats scissors. Okay. Okay, now whole new topic, and later we'll link them. In other words, graphs and strings. What's a string? Well, briefly, it's just it's a sequence of symbols, right? Like words, a string of letters. Binary string is just a string, like a sequence of binary digits, noughts and ones. Okay, so now strings, strings of characters, they might be letters of the Roman alphabet or Greek alphabet. They might be a sequence, a string of digits, like 1, 2, 3, 4, like a number, an integer, be a string of digits, for example. So the digits, the letters, they tend to go under the generic, general label of character. Right? They're just characters. So a string is just a sequence of characters, right? Just one after the other, with usually no spaces or commas or anything, just one symbol after the other. Now, here's another definition. What's an alphabet? Now, you're probably familiar with the usual man in the street definition of an alphabet, and of course they're linked. But in computer science, an alphabet has a technical meaning, a little bit different from the ordinary conversational meaning of the man in the street. Well, actually, the women in the street, because just for fun. Some recent research showed that the average woman, well, in the US at least, that's where the research was done, the average American woman, and I guess it's pretty general, most other countries, speaks something like 25,000 words a day, just in conversation. And the average man speaks about 15,000. So a lot less, okay, which probably doesn't surprise a lot of people. Anyway, so alphabet, in the technical sense, in computer science, an alphabet is just a list, it's a set of allowed symbols that you can use in your string. Right? So if you're saying, say you're forming binary strings, just a sequence of zeros and ones, well then your alphabet would just be 0, 1. Right? You only have 2 allowed symbols in your alphabet, your binary alphabet. If you're talking the Roman alphabet, you'd have 26 different symbols. In other words, the letters, A, B, C, D, ... X, Y, Z. Okay. So an alphabet, so it's a non-empty, finite set of characters, and those characters get used to make character strings. You just sequence one after the other to make a string, right? So the members of that alphabet are the characters you can use. We'll just we'll call them symbols. So character symbols, pretty much the same. So the members of your alphabet, they're the symbols of your alphabet that you use in your string. So symbols, character, much the same sort of thing. Now the alphabet, you can label an alphabet. You can identify an alphabet usually, and the convention is, well, in computer science, is to use a capital Greek letter. And here are 2 favourites that get used a lot, especially in the textbook by Sipser. One is sigma, and it's the capital sigma. Like the little sigma looks a bit like a 0 with a sort of a like curly. Well, it looks here. I'll draw it. This is little sigma. Right? It looks a bit like I'll do it here. Yeah, in that sort of orientation, that direction. That's little sigma. That wasn't so successful. Right? So that's capital sigma, and you see that, and in this context of theory of computation you think, an alphabet of symbols, or characters. Another favourite one is gamma. This is capital gamma. And what's little gamma? Little gamma. No, it doesn't matter. I think it's just a small version of this, isn't it? Can't remember. Anyway, so sigma and gamma, okay, as capitals, Greek letters. So they are two examples of labels for an alphabet. Alphabet in the sense of context of strings in computer science and theory of computation. All right. Now here's some examples of alphabets. I've mentioned this one a bit before, so we'll use capital sigma, right, to label an alphabet. And I'll call sigma 1. That's our first example of an alphabet. Now it's a set, right? It's a set of allowed symbols. So 0, 1. So that would then be the binary alphabet. Yeah, just two allowed symbols, 0 and 1. And here's an example of another alphabet, and the usual alphabet that we all know worldwide pretty well. Well, to the extent that the world's increasingly choosing English as the world.